Okay, so let's continue. Now the second part. To stationarity in autocorrelation. Okay, so what do I have? Let's say that I have this Ry process n minus k. The question is as follows. This is y of n minus k. Let me put the conjugate also, in case this is complex valued. Now the question is this a function of k only or not? So if I know k, can I always express the left side? I don't know n, but it doesn't depend on n. Okay. So that is the situation. Now we start with again two steps. Step number one. Okay. So let me calculate Rxy n minus k. Okay. So this is expected value of x of n, and I have, well, let me write this. Okay. Summation of k, but I have two k's. Let me be careful. This is k prime. Then h k prime x. This is n minus k prime, but n is n minus k prime. Okay, because this is y n minus k. N minus k. Actually, this should be the conjugate of this. Okay, so then I take the conjugate of this one and this one. Am I right? So this is y of n. Instead of n, I'm writing n minus k, but this dummy variable is also k prime. Okay, so if I take this expectation inside of this operation, so this is this, then what do I have? I have Rx, this is by the definition, n minus k prime. Am I right? Well, this is the autocorrelation of this x process. If I take this expectation inside, x of n times the second sampling time is this one, so it's this. Okay, but since this is Weissan stationary, you know, with some abuse of notation, I will write this as a function of a single argument. I think it will be clear because one of them is function of two arguments. This is the general one. But this one is x is Weissan stationary. Its autocorrelation does not depend on two arguments but their difference. So this is first one, this is minus the second one. So this is k plus k prime then. Okay? So there is some abuse of notation. These two functions have the same, let's say, name. Okay? But one of them is two arguments, the other one is second argument. But I think it's clear what we are trying to do. Okay. Now I'm at this instant, k prime, h conjugate, this, Rx, k plus this. So what's this k prime? Minus infinity to infinity. So what should I do? Well, this looks like a convolution, but it's not exactly like a convolution. So let me do a variable change. Okay. So first of all, this is something nice because I don't see any n's right now on the right hand side. So you see that this does not depend on n, so this function of k. Okay? Because k prime is just, you know, dummy variable of this summation, so this function of k. So let me write this as, to make it look like, you know, convolution, let me introduce, you know, because this will be k minus dummy variable. Then k double prime, so minus k. So this will be ranging from infinity to minus infinity. So h minus k, because double prime, Rx k minus k double prime. Let me put this kind of bracket for integer arguments. Okay. So is this clear what we are trying to do? So this now looks like a convolution. Okay, because dummy variable times another function k minus dummy variable. This argument is something like that. So how about this? This is looking, well, how do we do this, change of variables in these summations? This is a little tricky at the beginning, but can you find, for example, when k prime is equal to 5, I have a term like this, h conjugate 5 times rx k plus 5. Okay, so this is the same thing when k double prime is minus 5. K double prime, there is a minus 5 for this one. So I get the same term as you see. So the issue with these infinite summations is all of the term over here should appear on this one, and all the terms over here should appear on the other one. Okay? So this establishes that. So since summation is commutative, I can start from this end or that end, doesn't matter. So let me write it this way. Okay? So that is the deal. So these summations are a little bit more tricky than integrals, because sometimes you are very much used to integrals by change of variables, but sometimes you should make sure that these two summation inequalities are by considering all of these terms in the first summation and the second summation. There should be a one-to-one correspondence between those. So final result. So how do I say this? Now this is, let me say, Rxy of k, because this depends only on k. So how do I write this? H conjugate minus k convolution with Rx of k. Okay, so this is our final result. Okay, so what is this Rxyk? Now I see that this is this one. So I see there is no n dependence. Okay, which is good. Maybe I can make use of it later on. So this is the cross correlation. Now let's do the autocorrelation. This is second step, step 2, expected value of yn minus k conjugate. Okay. Step number 2. So how should I start this one? So let me write this one. So expected value yn k prime x h of k prime x n minus k, this is y of n, times y conjugate n minus, but let's be careful, k prime, this is k. Okay. So what did I do? Nothing new. This is y of n. That is it. Now let's move this expectation inside. So if I move this expectation inside, k, h of k prime, so I have Rxy, R, cross correlation of two processes, but I have already calculated exactly this thing. Well, for different sampling times, but this does not depend on the sampling time number 1 and sampling time number 2. It only depends on their difference. So I can use, this result, and I can call this as Rx of, now this is the second time, sampling time, T1 minus T2. Okay? K minus K prime. Sampling time 1, sampling time 2. This is the point where conjugates are useful, as you see. You can immediately understand that when I call xy, this is the second one with the conjugate. So my convention is T1 minus T2 as this delay. T1 minus T2 is K minus K prime. Okay? So this is even easier. Why it's even easier? So this is h of k convolution. So our impulse response is convolved with cross correlation, and indeed, this is Ry of k then, because there is no independence. Okay? So these are our two results. Ry of k, autocorrelation at the output, is expressed like this. Cross correlation. Well, cross correlation is expressed like that. So what is our conclusion? So y of n is y sense stationary, and x of n comma y of n is also jointly y sense stationary. So what was jointly y sense stationary definition? Individual processes should be y sense stationary, x and y. You see they are y sense stationary, and their cross correlation should be independent of, it should be function of lag only, as you see. This is what we have calculated. It should be independent of sampling times, or the origin of the sampling time. Okay, very good. Well, whenever you see these convolutions, of course you think about, as an electrical engineer, you think about transform domains. So if I have a convolution in the time domain, it corresponds to multiplication in a transform domain. But what kind of transform domain? Well, Fourier transform, isn't it? Convolutions and Fourier transforms, they interact very well with each other. So let me define over here, well, I'll first define it, but later on we will discuss its properties. Power spectral density, okay? First I will define it as a mathematical tool, then I will explain what is going on. Okay. So let me define, if I have Rx of k, so this is autocorrelation of a y sense stationary process. Okay? Well, now I will take its DTFT, discrete time Fourier transform. And I will call this S, X, e to the j omega. Okay? And I will call this as, this is something new, we haven't seen this, power spectral density. Okay, power spectral density of y sense stationary. This process has to be y sense stationary, otherwise you don't have, you have two variables and you cannot take its DTFT. Okay, so it's a function of only lag. I can take its DTFT and call it. I'll explain why do we call this power, spectral density, and so on. All of these three words are important. Of y sense stationary process, x of n. Okay, S x of e to the j omega. So let's remember what was Fourier transform definition. Okay, so this is R x of k e to the minus j omega k minus infinity, infinity. Okay, so this is, the forward transform. So let me write the inverse transform. Then Rx of k is 1 over 2 pi, 0 to 2 pi, Sx e to the j omega, e to the j omega k, d omega. There are so many things that we can say about Fourier transforms and so on. But, for example, one thing that we can say is, Sx e to the j omega as a being discrete time Fourier transform is a periodic function of omega with period 2 pi. So I don't have to take this integral over 0 to 2 pi, but any 2 pi interval is okay for me. Okay? So there are so many other things that we can say. But let's keep it at this point, but discuss this property in terms of Fourier transforms. So let me first make note of this. Notes. Number 1, Rxy of k. Let was this one. So I will make use of this convolution property of the Fourier transforms. This is h of minus k conjugate. This one. Now I'll write this one. Well, this is the same. Ry of k. Now h of k, but I want to write it like this. H of k convolution with Ry of k. So Ry of k is this, convolve with h of k. Now you see that Fourier transforms will be indeed useful. Okay? But to remember that, number one, what is the Fourier transform of this? So, what's the Fourier transform of that one? Okay, let's calculate this. So how should I develop a notation for this one? So let me write, for example, Fourier transform of h conjugate minus, let's say, n, something that we are more familiar, okay, with n variable. So this is, let me write DTFT, just to be exact. Okay, so this is the definition. And okay, so the classical trick, you should know these tricks very well. I should take the conjugate and conjugate one more time. Okay, so two conjugate of course cancel each other, but then this becomes n I have something like that. Then again I change my variable from here to here. N prime is equal to minus n. So again this is minus infinity to infinity. Oh no, I don't need it over here. So this is just because I am almost done. So this is h of conjugate. This is not present. This is okay. H of e to the j. This is minus omega. And there is a conjugate also over here. Okay. Because you know, this is standard Fourier transform with the variable minus omega. Okay, I have this. And there is a conjugate over here. Is this? Oh, okay. Sorry, I made a mistake at some point. This is, okay, let me correct this. This is not the result that I want. Okay, this point I have over here. And if I do this, yes, n prime is equal to minus n. E to the minus j omega n. And this conjugate is always present. At the beginning, I have forgotten to move this minus to the second line, okay? That was the issue. So if I have this minus n, I do this variable change. This is a prime variable, again minus infinity to infinity. And this is h of e to the j omega, just conjugate. Okay, that is it. Okay, now if I have that, what do I have? Now, if I substitute this result over here, then S, let's say xy, if I define something like that, So this is DTFT of Rxy of k. Let's say this is just a mathematical tool for our purposes. For now, I will explain the physical meaning of this later on. So it is the DTFT of this. So this is Sx e to the j omega Fourier transform of this times Fourier transform of this one. It is this. Okay. So this is number one. So Sy e to the j omega. This can also be written Yy. Then this is equal to DTFT of Ryy of k. So this is Sx e to the j omega times, this, H conjugate e to the j omega. Okay, this is this one. H e to the j omega. So I get so it's very interesting because I'm getting very compact results, as you see. So what do I see is the following. Output power spectral density, whatever its physical meaning is, this is output power spectral density. In Fourier domain, it is equal to the input power spectral density. Okay, this is a Fourier domain argument. So power spectral density is equal to the product of these two, meaning that input power spectral density times filters, let's say, magnitude response in square. Okay, this is the magnitude of the filter's response. So this is called magnitude response. Filter is, the impulse response previously we have defined as h of n. We have this. And we have also this cross-correlation result. Okay, something like this. Of course, they correspond to, Fourier domain descriptions of this autocorrelation and cross-correlation sequence. Okay, so let me also, in Z domain, I can do things like this. Also, in Z domain. Okay. So let me, maybe I can do this a little bit faster. So what is the Z transform of H conjugate minus N? Okay. I can do this calculation. I'll be writing here Z to the minus N, and I'll be writing these conjugates. And the final result will be, let me think, this is H conjugate 1 over Z conjugate. Okay, it will be something like that. Okay, where this is, now I'm in Z domain, Z transform of H of N. Okay, we say this definition. Okay, so I can do this calculation, but let's do a sanity check. When Z is equal to e to the j omega, okay, let's remember. Now Z transforms. So this is the complex plane for which this Z transform calculation is taking place. Maybe I should write these, some definitions. Okay, so this is Z transform definition. Okay, actually Z transform is easier to handle than Fourier transforms because you end up with polynomials, as you see. Okay, now I want to discuss the following. On the unit circle, let me move this circle, or this is like more like the center. Okay, this is the imaginary part. So this is the unit circle, meaning that this circle has radius 1, and this is the complex plane, as you see. And on the complex plane, if this angle is omega, this point is in the complex plane I can write this as e to the j omega. Okay? This part is cosine omega, this part is sine omega. So that point can be represented as e to the j omega, cosine plus j sine omega. Okay? So, as you may remember, as omega changes from 0, omega 0 is over here, omega is equal to, this is the omega also, where's this one? Okay. When omega moves to 180 degrees, omega is equal to 180 degrees, I move over here. This omega is equal to 90 degrees. So what am I trying to tell is, when z is equal to e to the j omega, I'm evaluating Fourier transform, okay? I'm evaluating this Fourier transform, exactly this one, without this part. When z is equal to e to the j omega. So as omega changes, I'm evaluating this z transform on the unit circle at different location as omega changes. That is the deal, okay? So, what else? So when z is equal to e to the j omega, let me insert it over here. Then I should get this result, special case. When z is equal to e to the j omega, I have e to the j omega conjugate over here, e to the j minus omega. But since this is a division, I get e to the j omega inside of this parentheses in the argument. So I exactly get that. And conjugate is also there. Okay, we are done. At least it's consistent. So how can I derive this? Well, the same thing. You put the conjugate over here. There is a minus over here. You put double conjugates like this. And you do the same operation. Okay, that is it. So, this is our result. But let me then write these in the z domain also. S, X, Y, Z. Actually, there is lots of abuse of notation. Sometimes it is this, sometimes it is that. But I think it's clear what we are trying to do. I don't want to invent different names for the same thing. Okay? So this is power spectral density one more time. But this time it is, let me write, Z transform of R, X, Y of K. Okay? Well, that is it. So this is the special case. Now what should I do? I should use this. So this is SXZ times, now this one, H conjugate 1 over Z conjugate. Okay. Now S, again in the special case I get this one. S, Y, Y, Z, or let me write it Y, Y this time. This is the Z transform of R, Y, Y, K. Right, R, Y, K. Because they are the same. You should get used to such notations. So this is X, X of Z times, this one, it is this. But let me write it like this. Okay. So this is equal to, let me use the same color. So I have this. Okay. This is also conjugated. Okay, so as I have said, when we have convolutions in play, transform domains can be useful, especially if you can identify your filter's magnitude response. Okay, this can be only the magnitude response of the filter is needed. So you can find this output power spectral density very easily by just multiplication. And if you take the inverse Fourier transform of this, you get output autocorrelation, which is good news. This is what we want to see perhaps, okay? An easy way of calculating autocorrelation. So this is another way of calculating output autocorrelation, but this involves convolutions. This is much easier, and so on. Okay, now I want to discuss this part in Z domain. What do you think about this? Let's say this is like the combination of two terms, combination of C, H combination of C. So this H of C times this. Now, if I tell you, this is something that you have seen in an earlier course. So this is, okay, imaginary part of z. Okay, z, real part of z. And let me say pole zero diagram. Pole zero diagram of h of c. Pole zero diagram. So how can I sketch this pole zero diagrams? Well, let me mark this unit circle because this can be important for stability and so on. Okay. Again, let me mark this as 1, this is -1, j, minus j. So let's say that I have a 0 over here, and let's say I have poles like this. Okay. So these are the pole locations, and this is the 0 location, as you have seen. Now, the question is, if I have such a filter, maybe there is a gain of this filter also. Gain is denoted as k. Let's say that k is equal to some number filter gain. Okay. Okay. So I can define, okay, let me write this. I think that's good enough. Okay, let's leave it at this point. Now, if this is h of z's pole zero diagram, now what is the pole zero diagram of this other term? Okay, let's think about this. For example, if this is at 1 over 2, so what do I see? I see the following from this diagram. H of 1 over 2 is equal to 0. Am I right? Because this is the 0 definition. So, let me see. Where is the other one? This is, let me use this one. Let's say this is P1. This is P1 conjugate. Okay? This point and the other is conjugate. So what does that mean? H of z, when z is equal to P1, is, let's say, singular. So let me write this infinite, but it's not good, but singular. Let me write, has a singularity. Okay? Or it also has a singularity at its conjugate also. Is this clear? So the transfer function blows up at P1 and P1 conjugate. Now the issue is this one. When does it blow up, or when it is equal to 0? Note that if h of is 0, let's say, okay, h of zk, let's say, is equal to 0, then h of h conjugate 1 over z conjugate is also equal to 0 when z is equal to what? 1 over zk conjugate. Do you see what I mean? So zk over here is, let's say, 1 over 2. So if this argument is 1 over 2, then this function is equal to 0. So this is the conjugate of this function. So if I take the conjugate of both parts, I get again 0. So this conjugate does not do anything. But if I can make this equal to zk, or 1 over 2, then this is equal to 0. Its conjugate will be equal to, again, 0. So how can I make this equal to this zk? Just insert this. Okay? So this is the 0 location. At this 0 location, zk, if I insert it over here, first conjugates cancel, then reciprocals cancel. I have hzk conjugate over, but that's also equal to 0. So what I see is the following. If I have a 0 at 1 over 2, the other one, let me mark this with, over here with blue. So there is a 0 at 2. Okay. Similarly, if there is a pole h pk, let me write this infinite, let's say, then is also infinite, 1 over pk conjugate. Okay, so h conjugate, or let me write h combination z, which is the product of these two, has poles and zeros in conjugate reciprocal pairs. So what is that one? That one. So conjugate reciprocal is this. If I have 0 at zk, then this implies that another 0 at 1 over zk conjugate. If I have a 0 or pole at zk, this is another pole. Okay? So there is a location. So this is what it says. If I have a pole over here at this P1 location, so 1 over P1 conjugate. Okay. So where is that one? 1 over P1 conjugate. Let me write this pole separately because I don't want to confuse you. If I have a pole at pk, this means another pole at 1 over pk conjugate. So how do I write this? 1 over magnitude of pk, and this is angle of pk. Because by complex numbers, pk is a complex number, so this is the magnitude of that complex number. There is an angle over here, but angle is conjugated. It's at the denominator. You move the angle up with plus sign. So what we see is, this is the magnitude of this P1. So this is inside of this unit circle. So this magnitude is less than 1. So 1 over magnitude is outside of this unit circle, but it is aligned, as you see. It is radially on the same line. Okay? So it has the same angle. So this is 1 over P1 conjugate. And similarly, there is 1 over, let's say P2 over here. Let me call this P2. 1 over P2 conjugate. This is the second pole. This is the first pole. And let me call this 0, 0, 1. This is 1 over 0, 1 conjugate. Okay? Is this clear? So these blue ones, let me mark this with this color, or let me use this color. This, and this are, these are pole zeros of H conjugate 1 over C conjugate. Okay? Because that was what I was trying to describe. So important thing is this definition maybe. Conjugate reciprocal pairs. Conjugate means this operation. Reciprocal means 1 over. So this is conjugate reciprocal pair. So this and this, they are paired. So if this is outside, apply this conjugate reciprocity, you get this inside. So that's the way it is. They appear in pairs. If it is on the real axis, of course the other one is also, because they have the same angle. Okay? I have something like that. Okay, why is this important? Because sometimes you have these filters not in Fourier-domain, but in Z transform. Okay, you have pole zero diagrams of these filters. Maybe you need to construct this. Okay, so this is the way you construct, conjugate reciprocal pairs. What else? Now, I will write very brief some properties of power spectral density, and that will be the end of this hour. So let me write, I will explain this in much more detail later on, but I want to mention this at this point. Power spectral density. So this is definition. DTFT. Well, number one, properties. Some of these properties are very easy. Well, Sx e to the j omega is real valued. Well, the reason is, since Rx of k is equal to Rx of minus k. So what is this? Well, remember, Rx of k is equal to expected value of x of n minus k. Okay? This is the definition. Again, let me put a conjugate outside of this. Let me conjugate also this inner part. I have two conjugates. So inside of this expectation, x conjugate, sorry, this is also conjugate. Okay, by the definition, x of n minus k. Now I have this definition. This is Rx, if I write this, x n minus k, x conjugate n conjugate. Okay? I have just moved this to the first position. The reason I am doing this is, please remember, this is the first sampling time, this is the second sampling time, because the conjugate is always on the second one. Okay? Now the difference. So this is T1, this is T2. T1 minus T2 is minus K. T1 minus T2. And there is a conjugate at this outside. So indeed, for this autocorrelation, because of this, I have such a equality. Okay? So autocorrelation is Hermitian symmetric. Rx of k is Hermitian symmetric. If this is real valued, it's just that conjugate does not do anything then Rx of k is an even function. So if this is, let's say, Hermitian symmetric, then, well, you can easily see that this would be real valued. Because if you take the conjugate of this, then I have conjugates over here, this is plus, then do a change of variable change, k to minus k, then this becomes minus, this becomes Rx conjugate minus k, but Rx conjugate minus k is equal to this. So you see that Sx conjugate e to the j omega is equal to Sx e to the j omega. So this function is equal to its conjugate, so it's real. Okay? So this is the way you do things. Okay, this was good. Number 2, Sx power spectral density is always, let's say, non-negative. Okay, I will prove this later, more on this later, because this is important for our purposes. So let's accept this for now. Number 3, so what is number 3? Area under Sx e to the j omega is the power this is important, of random process x of n. So what do I mean by this power of this random process? Power of random process. This is what we mean. Expected value of x of n second power. As I have said, in electrical engineering, this second power, also in physics, second power is very critical because, for example, Vc square, capacitor voltage square, okay? 1 over 2 C Vc square is the energy stored in the capacitor. So Vr square, resistance voltage square divided by R, current square, okay? So these are all energy and power quantities. So for this one, I am considering that this has, some, let me write this a little better, has units of volts. So this is like V square. Let's say that I'm applying this to a 1 ohm resistor. So you can say that this is the ensemble average of power, V square over R. Okay? So this is the power actually. This is what we mean. Okay, this is equal to actually Rx0 as you see. Autocorrelation, lag 0, Rx0 definition. Now, what is going on? So this is the explanation of this power of random process. Area under this. Well, this is some, okay. Rx of k is equal to inverse DTFT. Let me write this. DTFT inverse of Sx e to the j omega. Okay. So what is inverse DTFT? 1 over 2 pi. Let me say 0 to 2 pi. Sx e to the j omega plus j omega k d omega. That is the definition. Inverse DTFT. Now, when k is equal to 0, okay? So what do I have in that special case? Rx0 is equal to 1 over 2 pi, 0 to 2 pi, Sx e to the j omega d omega. So this is what I mean by this area. There is a 1 over 2 pi factor, but this is not very important. I can always, include this 1 over 2 pi factor if I wish into this definition, but I don't want to complicate my definition. So this is just appearing because of the Fourier transforms. So I call this area, okay? But as I have said, I could have defined this like 1 over 2 pi times this, then this would be, exactly the area, but I don't want to complicate my life. So at the end, what do I see? This power spectral density is something interesting. It's real valued. Okay. So Sx e to the j omega. Okay, it's real valued. And it's always non-negative. So it's periodic by 2 pi. So let me sketch this. Okay, let me sketch something like this. Then it repeats. This is a little smaller than that. Then it repeats. It also repeats over here. Okay. But very interesting. Non-negative. It can be 0, but it's never negative. The area. So if you calculate this area under this function, you get this ensemble power, you may say. Autocorrelation at 0th length, okay, of this process. So what does it say? Well, this tells you about, the power distribution, you may say, of this process in the spectrum, okay? Well, if you see a process like this, for example, power is equally distributed. So this is called, as you can imagine, white noise. Power is equally distributed, periodic by 2 pi one more time, at all frequencies. But let me make this, much higher, something like this. But in this case, you see that there is a resonant frequency at this point. Okay, so you see high power concentration around this neighborhood, also this neighborhood because of this periodicity, in comparison to these frequencies. Okay, so this power spectral density tells us things like that, but I will formulate this a lot more better. The reason I want to draw it right now, to convince you that this power spectral density definition, in spite of this transform domain calculations, this is basically the arithmetic of this operation. It's not very complicated, but this tells us something very important and useful with this definition. Okay, so these three properties are essential for that. Okay, so we will continue next time with more discussions. Okay, that's all for now.